Welcome back to Introduction to Software Reverse Engineering. In this module, we will explore structures in C, discuss some of their intrinsics when it comes to memory layout, and reverse engineer a new example program. Get ready for a lot of practical work today. Welcome to Module 11. In this module, we will talk about structures, their layout in memory, member packing, and padding. These concepts are very important for programming and compatibility of software, and they are also very important for reverse engineering. Let's start. There are a few goals I want to achieve in this module. First, review structures in C and talk about their important attributes, member alignment, padding, and packing. Second, I want to reverse engineer the most complex program we have seen so far. This program will require us to jump between two functions to reverse engineer not only those functions, but the layout of custom user-defined structure. And lastly, we will have one more chance to practice the skills developed in the modules dedicated to arrays. All materials covered in this course are available on GitHub. The link is on the screen and in the description below the video. In programming, it is often necessary to represent complex data entities that comprise multiple attributes. In C, structures provide the mechanisms for defining custom data types that can encapsulate diverse variables. A structure is a user-defined data type that allows you to combine variables of different types into a single unit. This enables you to create a cohesive representation of a data entity, such as an employee's information, which might include attributes like name, age, department, and salary. The key characteristics of structures are: they can contain multiple variables known as members or fields. These members can be of different data types, such as integers, characters, or floating point numbers. Structures are defined by the programmer to suit specific requirements. By utilizing structures, you can create more organized, readable, and maintainable code. This, in turn, facilitates efficient data management and manipulation, allowing you to tackle complex programming tasks with greater ease. Structures in C offer several benefits that make them a powerful tool for managing complex data. By grouping related data together, structures improve code organization and readability. This, in turn, makes it easier to understand and maintain your code. One of the key advantages of structures is that they can be passed to functions as a single unit. This simplifies data passing and reduces the need for multiple arguments, making your code more efficient and easier to work with. Structures are particularly useful in a variety of scenarios. For instance, they can be used to represent real-world entities, such as people, addresses, or products. They're also useful for storing and retrieving data from files, databases, or networks. In addition, structures play a crucial role in implementing complex algorithms, such as linked lists or trees. By using structures to represent nodes or elements, you can create sophisticated data structures that enable efficient data manipulation and retrieval. However, there is an important consideration to keep in mind when working with structures. The way structures are laid out in memory can have significant implications for performance and memory usage. Let's take a closer look at an example to illustrate this point. When a structure is stored in memory, the C compiler follows specific rules to determine its layout. Understanding these rules is crucial to working effectively with structures. First, members are stored in the order they are declared. The first member is placed at the starting address of the structure, and the subsequent members are stored after it. However, the compiler may add padding bytes to ensure proper alignment. Each member has a specific alignment requirement, which is typically the size of the member. If the current address doesn't meet this requirement, the compiler adds padding bytes to move the address to the next multiple of the alignment requirement. This alignment is important because different data types have different alignment requirements. For example, an integer might require a 4-byte alignment, while a character might only require a 1-byte alignment. It's worth noting that the layout of a structure can vary depending on the CPU architecture, operating system, and the compiler options. This means that the same structure might be laid out differently on different platforms. Understanding these nuances is essential to writing portable and efficient code. Let's explore the applications of structure layout and how it can affect your programs. When working with structures, it's often necessary to control how they are packed in memory. While the C standard doesn't specify how structures should be packed, many compilers provide extensions to control structure packing. These compiler-specific packing directives can be useful for optimizing memory usage and ensuring compatibility across different platforms. For example, you can use directives like pragma-pack push n to set the packing alignment to n bytes, and pragma-pack pop to restore the previous packing alignment. However, it is essential to use these directives judiciously. On one hand, tight packing can reduce memory usage by minimizing padding bytes. On the other hand, it can lead to slower performance due to misaligned access. When using packing directives, it's crucial to consider both memory usage and performance. Here are some best practices to keep in mind. Use package directives sparingly and only when necessary. Clearly document the use of package directives in your code. Thoroughly test your code on different platforms and compilers to ensure compatibility. By using package directives thoughtfully and following best practices, you can achieve fine-grained control over structure layout, optimize memory usage, and ensure compatibility with specific platforms or binary formats. It's time to start Ghidra. Import simple structures.exe example application and auto-analyze it. This is the program we will be reverse engineering this module. While the program is being analyzed, let's take a look at the source code of the first example. The source code lists a number of structure definitions that have exactly the same members. However, the structures use different pragma-pack compiler directives, including the default packing. This is the first function we will look into. It simply prints the sizes of the structures we just looked at a few seconds ago. However, before going to Ghidra to look at the decompiled code, let's take a short detour and look at the output of this function when the program is executed. The program's output is on the screen. The program's output is pretty verbose throughout its various functions. I highlighted the important part as it relates to the sizes of the structures. See that the size of the structures varies in the beginning when small values for packing are applied. Given we don't have large data types as members of the example structure, large values for packing directive do not influence the structures in a way that would bloat them with the necessary padding. Now, let's examine the same function in Ghidra. It is shown on the screen. First, fixing printf function signature is required to pull in missing function parameters. With the printf function signature correction or fix in place, the function looks almost exactly the same as in the source code, with the exception that the values are hexadecimal literals instead of size of operator. Now, let's switch attention to another example function. This function allocates a structure on the stack in a similar fashion to a variable of any basic types. Then, the function zeroes out the newly allocated structure variable, after which the variable is being populated by a getLocalTime function. And finally, the function prints out the current time. The decompiled version of the same function is shown on the screen. It is very self-explanatory and closely follows the original source code. The only difference is that the compiler optimized out filling all members of the structure with zeros by using function memset or zero memory macro and is explicitly clearing them. Ghidra has pretty good capabilities inferring structure types for non-function signatures. This is why a local10 variable automatically got system time data type. Let's switch gears and look at another example of custom structure and two functions that use this structure. The structure contains only two members, an integer value and a single precision floating point value. The functions are simple too. They're just showcasing the use of the structure in a similar fashion to the previous example. Let's take a look at the decompiled code of the second function from the previous screen, the one that allocates a structure variable and operates on it. Let's examine the function's body. First, see that on lines 9 and 10, variables of integer and float types are set to 0. Second, afterwards, only variable local10 is used in a function call on line 14. Third, both variables local10 and localc are used in the printing. Given the Ghidra doesn't know anything about the function's parameters for function shown on line 14, this code seems a bit confusing. Also, there is no sign of the original source code structure, just two independent variables. Let's explore function on line 14. The function that is updating the values within the structure is on the screen. See that it increments the value of the first item, line 5. And Ghidra shows a lot of type conversions for the second item, converting the value to a float and then back to an integer. This is a very common initial decompilation pattern for a few things. First, access to structure members through a pointer. Second, access to an array element through a pointer. And third, access to a C++ class member through a pointer. In this case, this is an example of access to a member of a structure through a pointer. Let's create a new structure in Ghidra. To do so, right-click on Simple Structures.exe in Data Type Manager window and select New Structure context menu element. The Structure Editor window will appear on the screen as shown right now. Change the structure definition as shown on the screen. Set the structure name and add two members, an integer and a float. Don't forget to save the changes before closing the window. With the new structure in place, let's utilize it. Bring up the Edit function window to modify its signature. Now, we need to modify the signature of this function so that it accepts a pointer to our newly created structure as a parameter, instead of a pointer to an integer. Modify the signature as shown on the screen and click OK to apply changes. With the change in place, the function will update and its body will perfectly match the original source code we looked at a few minutes ago. Now, let's go back to the previous function and see how it changed. This function was slightly changed. The newly created structure data type was propagated by Ghidra from the function's parameters to the type of local variable, as expected. Previously independent local variables are now structured as a part of the same instance of our custom structure local variable. Let's end this example here. Its reverse engineering is complete. Just as an array of integers can store multiple integer values, an array of structures can store multiple instances of a structure type. This means you can access and manipulate individual elements in an array using indexing, just like you would do with the basic types. The only difference when it comes to an array of structures is that unlike basic types, structures must be aligned. Therefore, they can be padded with empty bytes at the end. In this example, I want to reverse engineer the layout of the structure shown on the screen with the use of tools available in Ghidra, and discuss the discrepancies between the layout shown on the screen and the final result of reverse engineering. Also, we are going to look at the practical aspects of working with array of structures. See array declaration on the screen as well. The function we will start our reverse engineering exercise is shown on the screen. It is straightforward. The function iterates over an array of structures and prints the values stored in the path member of each array element, whether it's a file path or a directory path. The decompiled version of the function closely matches the source code with some minor changes. For example, the for loop is now presented as a do-while loop inside an if statement. Also, see that the pointer to an array is taken inside the body of the if statement and not always like in the source code. See line 11. Let's figure out the size of each structure, which is identical to the size of each array element in this case. Line 14 in the decompiled window shows 10C in hexadecimal, and the listing window agrees with that. At this point, it is safe to use the value of 10C hexadecimal as the size of the structure and continue reverse engineering. Create a new structure by right-clicking on simplestructure.exe in the Datatype Manager window and select New Structure context menu element. Set the new structure name as structure 0x10c in the structure editor. In the larger real-world reverse engineering undertakings, when the structure fields and the use of the structure is unknown, you'll need to be able to name a structure somehow. Therefore, coming up with the naming convention for structures of unknown use is a must. Then set the size of the structure to 10c hexadecimal, as we discovered a minute ago. Ghidra will fill the 10c bytes of the structure with single bytes for you. Save the changes and close the window for now. Now, it is possible to find the newly created structure in the list of the data types within the Datatype Manager window. At this point, let's check the format string of the printf function. It's a short format string. Change its type to a string. With the application of proper data type, we know that printf function accepts a string as one of its parameters to be printed out. However, how much of the 10c bytes of the structure this string occupies? All of it or some part of it? If only some part of it, what part? Let's dive deeper. Now, let's take a look at the data where Ghidra tells us the array begins. It's all just zeros here. Change the data type of this memory section to the newly created structure by right-clicking and selecting Data, choose Data Type context menu element. The Data Type Chooser dialog will appear on the screen. Type in structure 0x10c as the new data type and click OK to apply the change. Ghidra will update both windows, the decompile window and the listing window, to reflect the change. Now, let's change the data type once more and convert it into an array. Press open bracket hotkey to bring up Create Array window. Ghidra will suggest 50 elements as the starting point. Let's accept this suggestion and click OK to apply the change. Well, Ghidra was too aggressive with its suggestion. See that besides access to elements 0 and 1, there are accesses to elements 31, 32, 33, 34, and 35. This is an unusual pattern, unlikely to be implemented. Therefore, it's likely that the array is going way too far beyond its bounds. Let's leave it as is for now. We will come back to the task of finding the right size of the array in a few moments. At this point, there isn't much progress we can make here. Let's see the other function that uses the array for additional hints. The other function that uses the same array is shown on the screen, a part of it. The function is pretty large, and I will not go into the reverse engineering of all of it, but rather focus on particular points of interest. First, line 50 showcases the use of the structure from the array, and it's a named member at the offset 104 hexadecimal. Next, another interesting piece of data is the variable local 140, which is used as the source of data to populate our array of structures. This variable is of a known type, as it is used by the known Windows API functions find first file A and find next file A. See all highlighted uses of it. Now, let's inspect the use of the array pointer. See lines 50, 64, 85, 87, and 89. The interesting use of the pointer is on line 87, where one of the loop's exit conditions is located. First, see the use of familiar 10C structure size value. Second, on the same line, there is a memory address that lies beyond the array memory. Double-click on this address to see where it points in the program memory. The address points inside the 33rd element of the array. If the exit condition for the loop array iteration is checking whether the pointer is above or below this value, it is very likely that the array must end before this address. Now, let's go back to the line 50. Double-click on the array's name. Bring up the data chooser dialog to change the data type of the array. Change the size of the array to 32 elements. Click OK to apply the change. The decompile window should stay the same, but the listing window will change to reflect the new size of the array. Now, let's look at another use of the array's elements, line 94 and below. First, let's verify that 10C is still the correct increment value. It is. However, the decompile window shows only +1 on the line 101 for the pointer increment. This is the correct use of the pointer arithmetic in C. Now, see line 97. It checks if the value of a structure member at an offset 104 hexadecimal is 0 or not to determine if the value is a file or a directory. Also, note that the assembly instruction is test_al_al. The test is for the least significant 1 byte. This is a clue that the length of the structure member is 1 byte. To change the data type of the structure member, right-click on the field name and select Retype Field Context Menu option. The familiar data type chooser window will appear. Type in bool and click OK to apply the change. The field name has changed. Let's rename it to something meaningful. Right-click on the data member and select Rename Field from the context menu. The Rename Structure field window will appear showing the current field name. Type in isDirectory as the new field name and click OK to apply the change. This looks way better. Now, let's review the definition of the structure. Double-click on structure 0x10c in the Data Type Manager window. Now, find the isDirectory member. It is located at the offset 0x104. Let's go back to the use of this member in the code. See line 50. The structure is populated with a path to a file or a directory, but not through the pointer to a structure start, but through a pointer to the isDirectory member, and then with a negative offset of 104 hexadecimal or 260. This is somewhat common pattern for the Visual C++ compiler generated code. Let's go back to the structure definition and change the type of the first member to an array of 260 characters and set its name to name. Don't forget to click the Save button. Once the change is applied, the listing window will display the structure members in a more human-readable way. Now, let's go back to the function with which we started this analysis, the one that prints the file paths. The function uses a pointer that points to the name member of the structure of the first element of the array, which makes total sense. And, through the application of reverse engineering, we now know that this member is 260 characters long. In conclusion, let's review the reverse engineered layout of the structure. It has a 260 character long string, a boolean value, and 7 unused bytes. This unfortunately doesn't match the source code. Why? Let's talk about the discrepancies in the reverse engineering of this example program. First, the isDirectory member was aligned to 4 bytes, thus 3 padding bytes were added by the compiler. Second, the handle member was tucked in as the last member of the structure. Third, the member order is different in the reverse engineered structure because the first member was never used. And the program never used the real address where the array actually starts, 4 bytes prior to the start address we found. Fourth, also, this file path structure was never passed as an argument to another function where we could have a chance to examine the order of members on an individual basis. And lastly, there is unused and also padded space after the array, same 4 bytes. This makes it so that the array does not overlap with any other cross-reference, which would indicate incorrect starting address of the array in the memory. This is a big module, lots of information here. In the next module, we will review concept of nested structures and examine the ways structures can be passed as parameters to functions. Stay tuned! If you are looking to dive deeper into software reverse engineering, I'd like to recommend my book, Software Reverse Engineering: Navigating x86 Windows Applications with Ghidra. This course draws heavily from the book's content. However, the book itself contains many more examples and insights that can help developing your reverse engineering skills. The book is available in both print and digital Kindle versions on Amazon, making it easy to access and read wherever you are. Additionally, the book covers subjects not discussed in this course, such as reverse engineering of C++ programs, classes, virtual functions, and more. I encourage you to check it out. Thank you so much for watching and learning with me today. If you found this video helpful, please hit that like button and subscribe for more content like this. Your support means a lot to me. If you have any questions or topic you'd like to discuss, leave a comment below or shoot me an email. I'm happy to chat. If you'd like to support me and the channel financially, you can do so through Ko-fi or Patreon. Links are in the description below. Thanks again for watching, and I will see you in the next video.